This is section 5.4.1 on irrational numbers, simplifying, multiplying, and dividing square roots. First, we're going to define irrational numbers. The set of irrational numbers is the set of numbers whose decimal representations are neither terminating nor repeating. Here are a few examples of irrational numbers. The first is pi, probably the most popular, most commonly referenced. As you can see, pi is 3.141592 ... meaning that it never terminates. The next irrational number is phi. It is approximately 1.61803 ... because once again, it neither terminates nor repeats. And finally, the square root of 2 is an irrational number, because in decimal form, it is 1.41421 ... never terminating and never repeating. Our last example, the square root of 2, is a good example why today's lesson we're going to focus on simplifying, multiplying, and dividing square roots. Definition of square roots. The square root of a non-negative number n is the positive number that when multiplied by itself gives n. You can see the square root symbol here, the square root of n. And again, the definition is a non-negative number. So it has to be a positive number that when it's multiplied by itself, it gives n. So for example, 2 times 2 is 4, right? 2 being multiplied by itself gives us 4. So if we were to take the square root of 4, the square root of 4 is 2, simply because 2 times 2 is 4. So that's a good example that illustrates the definition of square roots. A perfect square is a number that is the square of a whole number. For example, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. These are our perfect squares because in order to get them, we can square a whole number. We know that when we square a number, that means we multiply it by itself. It's very important that you know your perfect squares. It will make working with square roots much easier. It's important to note that the square root of a perfect square is a whole number. For example, as I showed above, the square root of 4 is 2. Because 4 is a perfect square, the square root of 4 is a whole number, 2. Finally, we define the term radical. The square root of n includes the radical sign and the radicand. So the radical sign is what we often refer to as the square root sign or the square root symbol. We call this a radical. The radicand is the number under the square root symbol. So in this case, the radicand would be n. If we were taking the square root of 4, the radicand would be 4. Now we're ready to talk about simplifying square roots. Factor the radicand so that one of the factors is a perfect square. If a radicand does not have any perfect square factors, the radical cannot be simplified. All right, let's look at our examples below. We'll start with the square root of 75. So, first we're going to factor the radicand so that one of the factors is a perfect square. So our radicand in this case is 75. So we need to come up with factors of 75, one of which is a perfect square. You can see why it's important to know your perfect squares. If you know them well enough, you quickly realize that 25 is a perfect square, and if we multiply it by 3, we get 75. So we can rewrite the square root of 75 as the square root of 25 times 3. Next, we're going to actually take the square root of 25. So we can think of this now as written as the square root of 25 times the square root of 3. Well, since 25 is a perfect square, we can take the square root of 25, which is 5, because we know that 5 times 5 is 25. 3 is not a perfect square, so we cannot take the square root of 3, so we simply write it as the square root of 3. In fact, the square root of 3 is an irrational number, so its decimal form is never terminating, never repeating. We would much rather write it as the square root of 3 than a never terminating, never repeating decimal. So in the end, the square root of 75 simplifies to 5 square roots of 3. All right, our next example is the square root of 500. So again, we need to factor 500 into two numbers, one of which is a perfect square. Well, knowing that my perfect squares, I know that 10 times 10 is 100, so 100 is a perfect square, and 100 times 5 equals 500. Now I can take the square root of 100, because it's a perfect square. The square root of 100 is 10. I cannot take the square root of 5. It would be an irrational number. So the square root of 500 simplifies to 10 square roots of 5. Next we have the square root of 17. Hopefully you recognize 17 is a prime number, and it does not have any perfect square factors. So the square root of 17 is already in simplest form. We cannot change it anymore. Our final example is the square root of 25. And hopefully you recognize right off the bat that 25 is a perfect square because it's 5 times 5. So to take the square root of 25, we simply get the number 5. All right, next we're going to talk about multiplying square roots. The product of the square roots is the square root of the product of the radicands. Let's look at our examples. The square root of 2 times the square root of 5. So all we need to do when multiplying square roots is multiply the radicands and take the square root of them. So the square root of 2 times the square root of 5 is the square root of 2 times 5, which is 10. So we get the square root of 10. Now we always want to simplify our radical sign whenever possible. So we need to think, are there any perfect squares that are factors of 10? The answer here is no, there aren't. So the square root of 10 is our answer. Our second example, the square root of 7 times the square root of 7. So we're going to take the square root of 7 times 7. We know 7 times 7 is 49. The square root of 49, 49 is a perfect square, so the square root of 49 is just 7. And finally, we have the square root of 6 times the square root of 12. That's going to be the square root of 6 times 12, which is the square root of 72. Now, we need to ask ourselves, are there any perfect squares that are factors of 72? The answer is yes. And in fact, the largest perfect square that is a factor of 72 would be 36, because 36 times 2 is 72. 36 is a perfect square because it is 6 times 6. So when we take the square root of 36, we get 6. We cannot take the square root of 2 because it's an irrational number. And so we know that the square root of 6 times the square root of 12 equals 6 square roots of 2. Finally, dividing square roots. The quotient of two square roots is the square root of the quotient of the radicands. It's very similar to multiplying, except we're dividing. So let's look at our first example. The square root of 75 divided by the square root of 3 becomes the square root of 75 divided by 3. Well, we know that 75 divided by 3 is 25, so this becomes the square root of 25. And 25 is a perfect square, so the square root of 25 equals 5. Our second example, the square root of 90 divided by the square root of 2 becomes the square root of 90 divided by 2. 90 divided by 2 is 45, the square root of 45. Now we simplify. We know that the perfect square 9 goes into 45. The square root of 9 times 5. And since 9 is a perfect square, we can take the square root of it, and we can end up with 3 times the square root of 5. In our last example, 3 square roots of 15 divided by 5. So in this problem, it's important to note that there doesn't appear to be a number in front of the square root of 5, but in reality, it's a number 1. So we're going to separate this into two problems that are really one problem. We have 3 divided by 1, which is 3, and then we have the square root of 15 divided by the square root of 5. Well, we know that we can rewrite that as the square root of 15 divided by 5. And that 15 divided by 5 is 3. So in this case, we end up with 3 square roots of 3. And this concludes section 5.4.1 on irrational numbers, the simplifying, multiplying, and dividing of square roots.